Welcome back. In this video, I'm going to go through a few examples of standard error problems using the four formulas that I showed you in standard error part 3. And you might remember from the last section of this video that there are 4 different standard error formulas. So in our class, there are actually 4 different situations in which a standard error could be calculated, and each situation has its own formula. And we're going to go through at least one example of each of the 4 situations. The 4 situations are standard error for a mean with, standard error for a mean when the sample is and isn't more than 5% of the population, and also standard error for proportion when the sample is and isn't more than 5% of the population. Those are the 4 situations. So let's start with this as our first example. So here we have an imaginary random sampling situation. We're imagining that there's this population of 5 people, and these are the ages of the 5 people shown in the diagram. So the population has one 20-year-old, 3 25-year-olds, and one 30-year-old. And we're imagining that for some reason, someone is randomly selecting 3 of these people, recording their 3 ages, and calculating the mean age of the sample by adding and dividing by 3. And in this situation, we know that the population mean is 25. In other words, we know that the mean age of all 5 people in the population is 25. You could check that yourself if you wanted to. If you added these 5 ages, they would add up to, let's see, 25. They would add up to 125, and 125 divided by 5 would be the population mean of 25. But we don't know what the sample mean is going to come out to because it depends on which 3 people happen to be selected. For example, if these 3 25s happen to be selected, these 3 middle people, then the sample will have 3 25-year-olds and the sample mean will be 25. But if the sample ends up including 2 25s and 1 30, then the sample mean will come out to, well, let's see, 25 plus 25 is 50. 50 plus 30 is 80. 80 divided by 3 would be, let's see, I'm thinking 26.7, but I'd have to check that with a calculator. But I think that's what the sample mean would be with 2 25s and a 30. You can check me on that if you like. But I'm just trying to get across this idea that the sample mean will come out to some number, and it depends on which 3 people happen to be chosen. And what we want to do is, in this situation, is we want to get an idea of, we want to make an educated guess of how accurate the sample mean is going to be. In other words, we want to make an educated guess of how close the sample mean will be to 25, which is the population mean. And what we can do is calculate the standard error, because we can use the standard error to make an educated guess of how close the sample mean will be to 25. If the standard error comes out to a small number, then we'll say that the sample mean is likely to be close to 25. If the standard error comes out to a large number, we'll say that the sample mean is likely to come out far from 25. So remember that the standard error gives you an educated guess of how much error will occur in a random sampling situation. So if the standard error comes out to a small number, then you predict that the sample mean won't have very much error and that it's going to be pretty on target. But if the standard error comes out to a big number, you predict a larger amount of error, and you predict that the sample mean will be more off target, basically. So let's go ahead and try to calculate the standard error. So first we have to start with part A, which asks us if the sample is more than 5% of the population. So we can get this answer by dividing little n by capital N times 100. Remember, little n is sample size, capital N is population size. So in this case, we're taking a sample of 3 from a population of 5. So little n is 3, capital N is 5. So what it's going to be 3 divided by 5 times 100. 3 divided by 5 is 0.6, and 0.6 times 100 is 60%. So what this is telling us is that this sample of 3 people actually takes up 60% of the population. It's a pretty big piece of the population, and 60% is definitely more than 5. So the answer is yes, the sample will be more than 5% of the population. So now we can go ahead and do part B, and there's 2 pieces of information we have to keep in mind for part B. We have to know what statistic is being calculated with a random sample, and we also have to know our answer to part A. So we know that a sample mean is being calculated, and we know that the sample is more than 5% of the population. So we're going to be using the standard error formula for a sample mean when the sample is more than 5% of the population. And that's this formula right here. This is the appropriate formula for that situation. This part at the left, the sigma over square root of n, is actually the main part of the formula. This part right here that has the capital N under this square root is actually a correction that's always used when the sample is more than 5% of the population. So just think of this other part as being tacked on, basically, because of the fact that the sample is more than 5% of the population. If the sample wasn't more than 5% of the population, and if this answer had been no, then this second part would have been left out, and it would have just been the simple formula at the left. So let's try to plug in everything. So the population standard deviation is provided. It's 3.16. You could have actually calculated it yourself based on these 5 ages, but I just provided it to you. And little n right here is 3. That's the sample size. You could get that from the information over here, random sample of 3. Capital N is 5 because the sample is coming from a population of 5. So let's plug in all of those numbers. So we're really just plugging in 3 numbers: standard deviation, sample size, and population size, and this 1, which will always be there as part of the formula. So let's just try to work this out one step at a time. So first, let's do the work inside this square root sign right here. So 5 minus 3 is 2, 5 minus 1 is 4. So now we have 2/4 under the square root sign right here. Now let's divide 2 by 4. 2 divided by 4 is 0.5. So now we just have a single number under the square root. And the next step is for us to get the square root of 0.5 and the square root of 3. That way we just have 3 ordinary numbers to deal with. So the square root of 0.5 is 0.707. The square root of 3 is 1.732. So this is what we get after solving for the 2 square roots. And now let's divide the fraction. 3.16 divided by 1.732 would be 1.842. That times 0.707 would be 0.61. And that's the answer. That's the standard error for this situation. And now let's interpret what the standard error is telling us about the situation over here. So it's telling us that the sample is likely to be about 0.61 off target. And more specifically, it's telling us that the sample mean is likely to be about 0.61 from the population mean. And we know that the population mean is 25 in this situation from right here. So we could also say, we could also rephrase this and say the sample mean is likely to be about 0.61 away from 25. So so in this situation over here, if the sample mean came out to something like 25.5, that wouldn't be very surprising, because that would be 0.5 off target, and 0.5 is pretty close to 0.61. It's pretty close to what the standard error is predicting. If this sample mean happened to come out to 24.3, that would be 0.7 away from 25, and that also wouldn't be very surprising because 0.7 off target is pretty close to 0.61. So the standard error isn't saying that the sample mean is definitely going to be 0.61 from the population mean. It's just saying that it's likely to be somewhere in that general area. So now if the sample mean came out to, let's say, 29, we would be surprised because 29 is 4 away from 25. It's 4 off target from the population mean, and 4 is quite a bit bigger than 0.61. It's quite a bit more error than what the standard error is predicting. Now, a sample mean of 29 might be possible in this situation, but it wouldn't be likely. The standard error is telling us that the sample mean isn't likely to be that far off from the population mean. And before we move on, wanted to quickly mention that the words likely and about have to be included in this interpretation for it to be a correct interpretation. If you took out the word likely, or if you took out the word about, or if you took out both of those words, this interpretation would no longer be correct in part C. And just to see what I mean, let's try to take out one or both of the words and see what happens. If we take out the word likely, then this sentence would now say, the sample mean is definitely going to be about 0.61 from the population mean. And that wouldn't be correct because the sample mean isn't guaranteed to be about 0.61 from the population mean. It's just likely to be about that much. The sample mean could be, let's say, 1.5 from the population mean. That even though that might be unlikely, that could happen. So the sample mean is just likely to be about 0.61 from the population mean. It's not guaranteed. The error could be quite a bit more or quite a bit less. Now let's try to take out the word about and see what happens. If we take out the word about, then the sentence would say the sample mean is likely to be 0.61 from the population mean. Now, that would no longer be correct because the sample mean isn't likely to be exactly 0.61 from the population mean. Actually, it's not likely to be exactly 0.61 off target because that's just such a specific number. It's just likely to be about 0.61, not exactly 0.61. So you have to include the word likely and about for this to be a correct interpretation. Just giving you a heads up on that. So now let's move ahead to our next example. So here's problem number 2. We have a similar situation in which we have a population of a certain size, and the population has a mean and standard deviation that I'm providing, just hypothetically. And we're imagining someone is taking a random sample of 3 people from this population, recording their ages, and calculating the mean of the sample. So it's another imaginary random sampling situation. But in this case, the population is quite a bit larger. Instead of a population of 5, it's now a population of 10,000. So let's see if we can get the standard error for this situation. So in part A, we once again have to find out if the sample is more than 5% of the population using the same procedure. In this case, the answer is no because the sample is only 0.03% of the population. So that means we're going to be using the formula for standard error of a sample mean when the sample is not more than 5% of the population. Remember, the two things we have to pay attention to are what statistic is being calculated at the left end of the page, and also if the sample is more than 5% of the population. So here we have a sample mean being calculated, and the sample is not more than 5% of the population, which tells us that we need to be using this formula right here. And this is the same formula we had last time, except we're leaving off the correction that's needed we're leaving off the correction that's only needed when the sample is more than 5% of the population. So we're just using it's just the first piece of that formula we've already been using. So what we do is we plug in the population standard deviation, 3.16. This is sigma population standard deviation. Little n sample size is 3 because 3 people are being selected. And we just divide 3.16 by the square root of 3, just population standard deviation divided by square root of sample size. the square root of 3 is 1.732, and 3.16 divided by 1.732 is 1.82, rounded. So what we would say now is the sample mean is likely to be about 1.82 from the population mean. So we're using the same interpretation, but with just a different standard error, a different answer. So now let's move on to our third example. Here's our third example. So now we're back to another situation with a small population, shown as 5x's. In this case, it's a population of 5 people, and all 5 people have an age of 25. They all have the same age. And since the population has no dispersion, the population standard deviation is 0. And this is actually a special situation because in this situation, the standard error of the sample mean will actually be 0. If the standard deviation of the population is 0, the standard error will have to be 0. That's because when you take a random sample from this type of population and you calculate the mean of the sample mean has to match the population mean. So in this situation, the sample mean has to come out to 25 and match the population mean, because when the person randomly selects 3 people, it's definitely going to be three 25-year-olds, and 75 divided by 3 would be 25. So the sample mean has to be 25, and there's no chance for any sampling error at all. And if there's no chance for any error or any inaccuracy, the standard error or standard inaccuracy has to be 0. In this situation, the typical error or typical inaccuracy is 0. But we're going to go through the steps and actually see that the answer comes out to 0. So once again, in part A, we go through these steps. Little n divided by capital N times 100. In this case, it's a sample of 3 from a population of 5. 3 divided by 5 is 0.6. 0.6 times 100 would be 60%. So yeah, the sample will be 60% of the population, and that is more than 5%. 60 is more than 5. So we're back to using the longer version of the formula with this included. And when we have to go through all the same steps we did before, and we see that the answer comes out to 0, because 0 times anything is 0. So this is actually a special situation. So the way I would word this interpretation for this situation is the sample mean will be equal to the population mean, or some variation of that. So here I'm deviating from the typical wording that I would use, which is like the sample mean is likely to be about this far from the population mean. Usually I would use that type of a wording, but here it's a special situation, so I'm just using this wording. So now let's go ahead and move ahead to an example involving a proportion. Here we have a situation in which there's a population of 5 people, an imaginary population right here, and the population is 3 students and 2 non-students. So the population is basically 60% student and 40% non-student. And for some reason, a person is randomly selecting 3 people from the population, asking each person, are you a student? And then calculating the proportion of students within that sample of 3 people. So let's imagine for a moment that in the sample, let's imagine for a moment that the sample ends up being 1 student and 2 non-students. In that case, the proportion of students would be 1/3, or 0.33. Now let's imagine that in this situation, the sample ends up being 2 students and 1 non-student. Well, in that case, the sample proportion would end up being 0.67, or 2/3. So the proportion of students in the sample is going to come out to some number in this situation, depending on which 3 people happen to be selected. But what we care about is how close the sample proportion is going to be to the population proportion. So we know that the population proportion is 60% student. And what we want to know is um, how close is this sample proportion going to be to 60%? And that's what the standard error will help us answer. The standard error will help us get an answer to that question. So just like so before we were using the standard error to make an educated guess of how close a sample mean would be to a population mean, but now we're using the standard error to make an educated guess of how close a sample proportion will be to a population proportion. So now let's go to part A. Once again, little n divided by capital N times 100. Once again, 60% is more than 5%, so yes, the sample is more than 5% of the population. So now, once again, we have two pieces of information we have to pay attention to before we pick our formula. So we have to know what statistic we're calculating, or what statistic is being calculated in this imaginary situation, and also if the sample is more than 5% of the population. So in this imaginary situation, a proportion is being calculated, and the sample is more than 5% of the population. So that tells us that we're going to be using this formula right here. So right here at the left, we have the main formula for standard error of a proportion right here. And over here, we have the correction that's always used when the sample is more than 5% of the population, and it's just tacked on at the end. Notice how it's the same thing we've been using whenever the sample is more than 5% of the population. So like I said, it's just basically tacked on to the main formula. So over here, P is population proportion. So in this situation over here, the person is calculating the proportion of students within the sample. So what the person is trying to estimate is the proportion of students within the population. So the population proportion that's being estimated is 60%. So that's going to be our P over here. That's our population proportion is 60%. Basically, we're in this situation, the person who's taking the sample is focusing on students rather than non-students. So that's why the population proportion is 60% and not the 40%. So we plug in 60% right here, and we actually have to write it as a decimal. So 0.6. You could write 0.60, but it's the same. But 0.6 is the same thing. So it's the P, which came from over here, 60%. P times 1 minus P over the sample size of 3, which is the little n right here. So, and over here, we have population size minus sample size and population size minus 1. So we just have to work on these one part at a time. So let's start at the left end. So 1 minus 0.6 would be 0.4. 0.6 times 0.4 would be 0.24. And then 0.24 divided by 3 would be 0.08. So at this point, we have one number under the square root, and it's just 0.08. And then, so basically this part is just the square root of 0.08, whatever that happens to be. Over here, 5 minus 3 would be 2. 5 minus 1 would be 4. So we would be 2/4 under the square root right here. 2 divided by 4 would be 0.5. So here we have the square root of 0.5. And so basically what we have here is the square root of 0.08 and the square root of 0.5. Multiply those two numbers and you'll get your answer. This is what it is rounded. It's 0.20. And I wasn't able to show a complete breakdown of all of the steps, but I actually have another video that I recorded last semester that shows a more detailed breakdown of the steps, if that would be helpful to you. It actually doesn't have any sound, but it does show all of the small steps along the way. So I'll actually provide that as a part 5 video that'll be optional if you want to look at that. So now let's move ahead to part C. Well, we have the same type of interpretation, except instead of saying sample mean, we're saying sample proportion, because instead of reaching a conclusion about how close a sample mean is likely to be to a population mean, we're reaching a conclusion about how close a sample proportion is likely to be to a population proportion. So the word sample mean is being replaced by sample proportion, and population mean is being replaced by population proportion. Otherwise, it's the same exact wording. So basically, when the sample mean is calculated, when the sample proportion is calculated, it's likely to come out roughly 0.2 away from the population proportion, which, as we know, is 0.60. Okay, now let's move ahead to our last example. Here we have another example involving proportions. So here we have a population of 10,000 people, and we're imagining that this population is 15% student. And for some reason, a person is taking a random sample of 3 people and asking each person, "Are you a student?" and recording their 3 answers, and then calculating the proportion of students within the sample. And the sample proportion will once again come out to some number depending on which 3 people happen to be selected. But we want to know is, once again, how close the sample proportion will be to the population proportion. We want to know how close this number is going to be to 15%. So the standard error will help us again. So once again, in part A, we go through these steps, and this time, no, the sample is not more than 5% of the population, because 0.03 is definitely less than 5, so it's not more than 5% of the population. And that means we take off the correction that's only needed when the sample is more than 5% of the population, and we just stick with the shorter version of the formula. So this is the short version for the proportion standard error. So P times 1 minus P over N. So we know that the population is 15% student, and this is the number that this person is focusing on, or basically this is the statistic that this person is interested in estimating. So that's our population proportion. We have to turn it to a decimal, so it's 0.15. So 0.15 times 1 minus 0.15 over 3, which is our little n sample size. It's provided over here. So it's going to be 1 minus 0.15, which is 0.85. 0.85 times 0.15. Once you get that answer, divide by 3. Then finally get the square root, and you have your standard error. It's 0.21, rounded, which just is telling us that the sample proportion is likely to come out to something about 0.21 away from the population proportion. In other words, it's likely to come out to about 0.21 away from 0.15. And that's the last example. So we've covered all 4 situations. We've covered standard error for a mean, when the sample is and isn't more than 5%, and standard error for proportion, when the sample is and isn't more than 5%. So just let me know if you have any questions, and that's it for this video.